Hi everyone, welcome to the first astronomy talk of this academic year. Tonight, we are very honored to have Professor Alan Heavens with us to give a talk titled Einstein's Biggest Blunder, Does the Cosmological Constant Exist? Before we begin, here's a short introduction about our speaker. Professor Alan Heavens is currently the chair of Astrostatics and the director of Imperial Centre for Interference and Cosmology at the Imperial College London. Having completed his PhD and master's degree here at Cambridge, Professor on Astrophysics at University of Cambridge from 1977 to 1983. His research interests include developing and applying the best methods for extracting information from data, non-Gaussianity in the cosmological microwave background and in the galaxy distribution, and whether or not the acceleration of universe is due to Einstein's cosmological constant, dark energy, or alternative gravity models. Now, without further waffle, Professor Alan Heavens, please.
Thank you very much for that nice introduction. It's very nice to be back. I was going to talk today about Einstein's biggest blunder and where we are in trying to understand whether he did in fact make a mistake all those years ago. So it's partly going to be history, it's partly going to be a description of our understanding at the moment. But the question that we're trying to answer is, what is the cause of the acceleration of the universe? Something which was discovered, if you like, in the very late 90s, and which was something of a surprise. And the reason for that is something which we're trying to get to the bottom of in research these days. And I'm going to end up with just talking a little bit about the research that we do to try to answer this question and related questions using statistics in a way that we hope is going to extract everything out of the data that we possibly can. So let's go back in history to, wait, no. Hang on, let's see, okay, how that works, right, we're fine. Going back in history about to look at the development of gravity theory is, of course, perhaps the most important time was in the early 20th century when Einstein's theory was new. And the alternative was Newton's long-established theory. And there was a very famous experiment in 1919 to test whether Newton was right or Einstein was right. And the test that was done was to look at the bending of light around a massive body, in this case, the sun. And in Einstein's theory, the theory can be divided into two parts. One says that matter tells space-time how to curve, and then in a curved space-time, the curved space-time tells matter how to move. And you can divide the theory sort of logically into these two parts. And the idea was to apply this to light, where light from a distant star, when it passed close to the sun, would get bent and would appear to be coming from position B. And it turns out that Einstein's theory predicts that the bending angle should be exactly twice what Newton would predict. And here's a sketch from the expedition. It was done during a total eclipse, which a moment's thought will tell you why it has to be done during a total eclipse, because you want to see the stars which are very close to the limb of the sun, so you've got to block the light out from the sun. And there was conveniently an eclipse in 1919 whose totality passed over Brazil and then over an island called Principe, just off the coast of Africa. And Sir Arthur Eddington organized expeditions to both of these places, where they took photographs of the positions of the stars during the total solar eclipse and then compared them indirectly, as it turns out, with other photographs taken when the sun had been allowed to move away to another part of the sky. So this is what they saw. Well, it's not what they saw. This is a BBC version where the displacements of the stars have been exaggerated by a factor of 50 in order for you to be able to see them. But you can see that the stars, when the eclipse was happening, the stars appeared at distances which were larger than when the sun was not in the way. So here's some pictures of the Brazilian part of this. This is a photograph of the eclipse. There's a couple of stars there that you probably can't see here. And we're looking for slight shifts. This is one of the stars, so that's the seeing disk, and that's the shift that they were looking for. So pretty small, pretty difficult experiment to do. All sorts of things that you need to worry about whether the photographic plates have got damp or got heated up and got distorted. So lots of things that you have to worry about. But they did, given the challenges, they did a pretty good job. This is the paper by Dyson et al. And it's actually quite an interesting exercise. I set it as an exercise for statistics students to deduce what the bending angle is by using statistical sampling techniques. And this is one of the codes that gives you the bend angle. And this favors Einstein. You have to worry about all sorts of things because you're comparing two plates. In fact, they compared three, but and you want to look for displacements. So you have to worry about whether your plates are centered correctly, whether they're rotated, whether one of them has got heated up and expanded. So there's all sorts of things which we call nuisance parameters that are part of the analysis, but that you have to worry about. And that's what all of these other things are down here. But the crucial one is this one, which is tells you whether Einstein was right. And although this is a slightly controversial experiment, some people think that it didn't really show that Einstein was right. But I think reanalyzing their data, I think it's pretty clear that it did favor Einstein over Newton. So Einstein's theory looked in good shape. In fact, Einstein was very pleased with the results from the experiment. Here's a letter, a postcard that he wrote to his mother, which I'll translate for you. It says, "Liebe Mutter, dear mother." And then actually I don't speak German, so that's as much as and it was reported in the press at the time. Here's a sketch of the displacement. You can see it's difficult. It's not a very simple movement of the stars away because it's the measurements are very noisy. So there's a lot of noise in the results and the sorts of things you need to worry about. But it was reported in the New York Times, like all the skew in the heavens. But you'll be reassured to know that the stars are not where they seemed or were calculated to be, but nobody need worry. So Einstein's theory, which is the one that we currently use, has been tested in many different ways. So I wanted to go through some of the tests. This is the Pound-Repke experiment, where if you have iron emitting light at the bottom, then it loses energy as the light loses energy when you get to the top. So it's measured with a different frequency, and the difference in frequency when multiplied by h, I guess, is the difference in potential energy. So this is one of the rather benign tests of gravity, because more or less any theory of gravity will give you this, that if it's lost potential energy in going from the bottom of the lab to the top, then it's going to change its frequency. But at least it passed this test. Other ones that I'm sure you're aware of the precession of the perihelion of Mercury is another one. We know that in Newtonian orbits around a point mass, then a particle or a planet would go round in an elliptical orbit and go round in the same orbit repeatedly. But in Einstein's theory, that doesn't happen, and the orbit precesses, and you can see a very exaggerated precession here of subsequent orbits. The orientation of the elliptical orbit gradually moves around. And in Einstein's theory, you can predict what that precession should be, and it's very small. It's 43 arc seconds per century. So that's the angle of the major axis, say, as it moves around. It moves through at a rate of 43 arc seconds per century. And surprisingly, to me at least, even in the late 19th century, precessions could be measured with accuracies of 1 arcsecond per century, which is, I think, astonishing for those times. So that's the prediction. What was measured was that it's about 5,600 arcseconds per century. It doesn't look very good for Einstein at the moment, but of course, the solar system is not just the sun and one planet going around in orbit. There's all sorts of other stuff there, including some reasonably massive things like Jupiter, which perturb the orbit, and so they cause a precession. And if you calculate, as they were able to do in those days, what the precession due to the other planets, principally Jupiter and Saturn, of course, would cause, it causes all but 43 arcseconds of that 5,600. So, so it passes this this test as well. Of course, the fact that other planets can cause precession led people to think that, well, maybe we've just missed a planet, and there's another planet in the solar system that's causing this 43 arcseconds per century precession. So they even gave it a name called Vulcan, and they could work out where it should be, which is also quite impressive, I think, from a theoretical point of view. Now, this was done by Leverrier. Leverrier, you may know, had worked out the presence of Neptune because of perturbations in Uranus's orbit. So he had a good history of being able to predict the presence of previously undiscovered planets. So they knew what its orbit should be if it was going to account for the 43 arcseconds per century. And they found out that, in fact, it should be, I think it should be within the orbit of Mercury, if I remember, but every so often it should go across the face of the sun in a transit, like this one shown here, transit of Venus, I think. So they knew when it was going to happen, and so many telescopes were pointed at the sun at the appropriate time, and nothing appeared. So it didn't appear. Fortunately, Leverrier died just before the experiment, so he never knew. But it wasn't there, and there was no explanation in terms of another planet. So it passes this test as well. There have been others since. Time delay measurements. The time passes a bit slowly when you're close to a large mass like the sun. So if you time how long it takes to send a radar signal to Venus across the solar system and back again, you're going to get a slightly different answer from what you would get with Newtonian gravity. And there's also the fact that the light is bent a bit as well, so you have to take into account both of those. And that's been tested very well, and this is the signal that you would expect in general relativity for the time delay in microseconds. This is about 10 to the minus 4 seconds at the maximum, and it's been done over the years, and you can see that it gives works very nicely. So Einstein's theory has been tested quite well. This one to a precision of about, what's that, 1 part in 10 to the 5 or so. But there's other ones, more recent ones, like Gravity Probe B, which has tested some of the more subtle differences that you get. There's if you have a rotating body, then it tends to, in some loose sense, drag space-time around with it a little bit, and you can measure that, and that's been measured with Gravity Probe B. Not with great precision, but with agreement for GR, and you can also check the movement of a vector in a curved space-time is also slightly complicated, and that's a geodetic effect, which was also tested with Gravity Probe B. So Einstein's theory looks in good shape from the experimental point of view, but all of these tests are done in very weak fields. So the gravitational field, by some dimensionless argument, is very weak in the vicinity of the sun. So looking for strong field effects is much more interesting. And as you're aware, gravitational waves has been the recent beautiful verification of general relativity from in spiraling black holes, and in one case with a neutron star in the orbit. And in black holes, then the fields are extremely strong. So this is a strong gravitational field test of general relativity. And this diagram shows, I think the colored bits show the rate at which time is passing in the space-time. So the yellow parts are where the time is flowing relatively slowly. And here they slowed it down to just the point where the two black holes merge, and then they wobble around a bit. And whilst they're doing this, then they emit gravitational waves. So gravitational waves are a simultaneous stretching and squeezing. So they'll squeeze in one direction simultaneously with stretching in another direction. And this amazing experiment that is clearly, if you think about it as a physicist for a moment, it's clearly impossible to detect gravitational waves, but they did it. And these are the signals that they got from the LIGO detectors, showing a really nice agreement with the equally impressive theoretical calculations of what you should get out from a system like this. And the measurements are not perfect and noisy, but showing really nice agreement with theory. So that's a nice test of gravitational of general relativity in a stronger field. So everything looks fine, but what's the problem then? Well, the problem, as you're aware, is that in Einstein's first manifestation of general relativity, you can't have a static universe. And the reason is relatively simple, that if you take a sphere of the universe, let's assume that we're at the center of the sphere, then with Newtonian theory, and indeed with Einstein's theory as well, if you want to know what happens to the surface of this, then you need to consider only the mass inside the sphere, a thing called Birkhoff's theorem. And of course, if it's gravity, it's going to pull the thing in. So you can't keep this thing static unless you have a balancing force. So what Einstein did was to introduce into his equations this extra term, the cosmological constant, to balance this out. Turns out to be a very bad idea. It wasn't one of Einstein's best, I have to say, because it doesn't do what it's supposed to do. You can set this up so that the forces balance, but it's unstable. So any slight perturbation to this, if it gets compressed, then gravity is going to win and it's going to collapse. If it expands, then the lambda force is going to win and it's going to expand to infinity. So it wasn't the best solution, and that's possibly one of the reasons why Einstein didn't like it. Another one is that the universe is not static. That was the other thing that made this lambda term unnecessary. And he apparently said it was the greatest blunder to include it. But once it's in the theory, then it's in the theory and you can't really take it out. So it's existed ever since. It was ignored for a long time, but only in the last decades of the last century, people began to take notice of it. But in the early days of the last century, the static universe was something which was had been considered, but the observations didn't bear it out. Does anybody know who this is? Any ideas about? So this is the person who discovered the expansion of the universe, and his name is Schleifer. You may be thinking Hubble, but it's not Hubble. Schleifer made observations of the radial velocities of nearby galaxies, and by looking at the spectral lines and the Doppler shifts, what he found was that the nearby galaxies, with just a few exceptions, all had positive velocities, which meant that they were moving away from the Earth, and very few of them were moving towards it. So we understand why a few of them are moving towards it nowadays. But he really showed that, yeah, actually pretty much everything was moving away from us. So the universe was not static. And this is some of the data. These are basically spectra. So if these were color plates, this would be the blue end of the spectrum here and the red end of the spectrum here. And you can see these absorption lines of calcium, H and K here. And as you look further down, you see these two dark absorption lines moving further and further towards the red end of the spectrum. And these indicating that these things are moving away. So Hubble's contribution was that he could work out the distances to these things using some standard candles, which are Cepheid variables, where the period of the oscillation of the Cepheid variables is related to their luminosity. So if you measure the period, it tells you what the absolute brightness, luminosity of the source is. So by looking to see how faint they appear to be, you can work out the distances. So he was able to provide distances, and then you could plot one against the other. This one is Hubble, showing a beautiful straight line between the distance and the velocity. Well, perfect, but there's clearly a trend there. And as I say, nowadays we understand why it's not a perfect straight line. But so he found this straight line relationship between the recession speed and the distance, called Hubble's law. So Einstein did not know this. So he was trying to find a theory which would account for a steady state or a steady static universe, but in fact it wasn't. So he was a bit unlucky, I think, because I think this chap, I don't know whether you recognize him or not, but if he could have predicted the expansion of the universe, because his GR theory didn't allow for a static universe. So if he'd been smart, he would have said, look, my theory, which I believe in, doesn't allow a static universe. The universe must be expanding or contracting. So, he could have been famous if he just made that last step. But he lost confidence and put in this lambda term. Whoops. I messed that up. Is this going to mess everything up? Sorry. I just pressed the wrong button.
What did you do?
I think it was in the window, that's right, and then we made it
Large.
Then did we make that larger? That's right.
And then could you go back to Zoom and show us?
So
Oh, no, it's fine.
is it fine?
Wait, what can I do?
Yeah.
Thanks.
No, we have to display it again. No, I need to display it for a moment.
Oh.
So, so we could do that. Is it sharing? Can you ask somebody online? It's not.
Perfect. Done.
Okay.
Does that work?
No, we're displaying the wrong one.
Let me check.
Is it okay? Right, sorry about that. So you want to hide the floating heating controls? Okay. Is that all right?
Apologies while we're being plagued by a tech.
Oh no.
Yeah. They didn't warn us that this was a new system.
Okay. We're in business here, at least on one aspect.
All right, all good.
Good.
I think.
Is it okay online? All right, sorry about that. I'll keep my fat fingers away from that button. So what's the picture that we should have of this that represents Hubble's law? Well, this is it really. So if we take a patch of the universe with this illustration and imagine that we're somewhere, I think this big bright star here, and then look at it very slightly later, everything has moved apart with a speed which is proportional to distance. So what that corresponds to really is just changing the zoom setting of the two pictures and overlaying them. And what you'll see here is that the nearby things have moved a little bit, but the ones that are further away from us have moved further. So if this was 2 snapshots, then we would conclude that the velocity of these 2 was this one was rather small and this was rather large, and that's just something that we law. But this looks as though we have a special place here at the center of the universe. But you can play this experiment, do this experiment wherever you like, and imagine that we were somewhere up in the top right. So let's imagine that we were here. If you do the same exercise, then you find exactly the same Hubble law. So everywhere in the universe would see this velocity proportional to distance. So the only change here is that I've kept the fixed point to be over here rather than over here. But you see exactly the same velocity proportional to distance in this picture as well. So let's just think logically about what this means. If we were to, so this shows the Hubble expansion. So I'll just go back. So there's 1 million light years between these 2 and 2 million light years between these 2. As the universe expands, then the 1 million becomes 2 million and the 2 million becomes 4 million. So this one's moved by 1 unit, this one's moved by 2. So the velocity of the blue one is twice that of the green one. But if we were to run time backwards, then at some point in the past, everything may have been on top of each other in an infinite density situation. And something, we don't really quite know what, sent the constituents of the universe moving apart at high speed. And that event is called the Big Bang, of course. So that was the theory before lambda was considered important. So that's quite a big extrapolation to say let's run things backwards until the universe was infinitely dense. So we should ask for a bit more evidence that this actually happened, and we can get that from the first few minutes after the Big Bang, when the universe was extremely dense and extremely hot. And in those situations, the high density of the universe and the high velocities of the hot particles allow nuclear reactions to take place and the light elements to be built up. After a few minutes, the atoms or the nuclei are too far apart to interact significantly. So all of this happens in the first few minutes, and you can get just the light elements this way, including lithium. Lithium's interesting because the lithium that you get in your batteries is pretty much all of it will have been made a few minutes after the Big Bang. It's a good job that we got this. This was made 13.8 billion years ago. We got it just in time because, as you see, you have to use it by it would have been useless after that. So you can look at the abundances of the light elements and compare with what you would expect theoretically. And the yield that you get of the different elements depends on what the density of ordinary matter is. The more ordinary matter you have, the more collisions you'll have, the more light elements you will make. In some cases, you destroy some more, but you can predict what should be the outcome after the first 3 minutes and compare it with what you see. And you get pretty good agreement with the amount of hydrogen here, the amount of helium-3 here, and the amount of deuterium, provided that the density of ordinary matter is somewhere near this vertical gray bar. And that tells you how much ordinary matter there is in the universe. And it's not very much. It turns out to be about 4 or 5% of the total energy in the universe is in the form of ordinary matter. So any more evidence? Well, we talked about the matter that's left over from the Big Bang. We can also talk about the light that's left over from the Big Bang. Big Bang was hot, so there's radiation involved, and we see that now. It's now cooled to 2.7 Kelvin. This is from the Planck satellite. And this shows the temperature of the universe. After subtracting off a big dipole that comes from the fact that we're moving through the universe at a few hundred kilometers a second. So this is basically a uniform temperature to within about 1 part in 10 to the 5. We'll come back to what it tells us in a moment. So we have plenty of evidence that the Big Bang happened, but we have this strange thing that the amount of ordinary matter is rather small. So let's ask what happens next? What happens as the universe evolves? And this is a computer simulation of the clustering of matter. You saw that the universe was not quite uniform from the distribution of light. Those fluctuations in the light density are associated with fluctuations in the dark matter density, and that's an instability that the dense parts of the universe will pull in more matter and get denser. So you have structures forming, and this is an example of a simulation of structure formation. You can also do more complicated simulations that try to include star formation and all sorts of things. So it's, we now have increasingly sophisticated ways of predicting what the universe has been, working out what the universe has been doing over time. So this is the picture that we have. We have the Big Bang at the left. This is time going left to right. Some things set the constituents going apart. We have nuclear synthesis right at the beginning here. At some point, the universe gets transparent to radiation, and that's where we see the microwave background radiation from. Around about 400,000 years after the Big Bang, it becomes transparent. And then not much happens for a while, and then the structures begin to form, and we get the rich sequence of galaxies, galaxy clusters, and so on, until we get to today. So everything seemed all right in the 1990s, but then this surprise came, and the surprise was that by looking at exploding stars like this, something strange happened. So this is a model for a supernova explosion, where you have a binary star where some of the mass from the companion lands on this star. At a certain point, the gravity is so strong that nothing can support it, and it collapses. And in collapsing, it also leads to an explosion. So if you dump matter onto a white dwarf star like this, then something like this happens. The star explodes into a supernova explosion, and this thing is for a short time, days or weeks, extremely bright, like a billion times brighter than the sun. So one of these things can outshine an entire galaxy. So they're very useful for two reasons. One is that they're really bright, so you can see them a long distance away. And the other is that they're all more or less the same. They just accumulate matter until gravity can't be resisted, and then they collapse. So in rough terms, I mean, I think there's lots of details that one needs to worry about, but basically they're all essentially the same mass, give or take. So they count as things called standard candles. Now, standard candles like the Cepheids are useful because we can work out the distances to them. If they all have the same luminosity, then you can use basically a cosmological version of the inverse square law to work out how far away they are. So that's very useful. And then you could do experiments like this. So this is, let's imagine that we lived in a universe which was not accelerating or decelerating. Everything's just going out at constant speed. So we still have Hubble's law. So one individual galaxy would in this case, keep its velocity. It would stay receding at the same velocity, but not all galaxies have the same velocity. And we can ask, well, what would if we plot the distance and the speed, then here's Hubble's law with the line here. Let's consider this object here. Now we have to think about this a little bit harder, because this object is a long way away. And we're seeing the light from it, and light travels at a finite speed. So we see this object at an earlier stage in the universe. So what we expect to happen with Einstein's original version of his theory is that the universe should decelerate. So in comparison with this situation where the galaxy neither decelerates nor accelerates, we would expect to see it on the right. So it should have been, since we're looking at it in the past, if things have been slowing down, it would have been moving faster when we saw it. So we expect that if we plotted this graph for a whole load of different objects, we would expect the distant ones to be to the right of the line, and the ones which are close to us, where we're seeing them almost at the current time, they wouldn't slow down very much. So we expect to see a line that curves to the right, and but this is what you see. Is what happened in the late 90s. 2 experiments did this with supernovae. The non-accelerating, non-decelerating line is the top red line, and you can maybe convince yourself that the majority of these points are sitting, it looks like above the line. I like to think of it as being to the left of the line, that they were moving more slowly than if they hadn't been accelerating or decelerating. So they're slightly to the left of the line. It's noisy. There are some to the right, but predominantly they're to the left of the line, which indicates that the universe is now accelerating rather than decelerating, which is totally against what you expect with ordinary gravity. So they're on that side. So this was significant enough that these guys got awarded the Nobel Prize for it in 2011. So that was the first strong evidence. There were hints before. In fact, George Eustathiou here was instrumental in suggesting that lambda might be important before these experiments. But I think these were the ones that I think really meant that everybody took notice and thought that maybe lambda was actually right, because as we'll see, lambda is one way of explaining this. Other things that we can do, we can check standard rulers. So again, if we've got other methods to measure distances. I think in the interest of time, I won't give an explanation of that. But what we can do then is to work out if we plot what these experiments imply for the amount of matter in the universe and the amount of lambda, then the supernovae restrict you to this blue area. These so-called baryon acoustic oscillation restrict you to this green part. And then there's the CMB that we just saw that tells us something else as well. And what that can tell you is that if you look at what you expect for the geometry of the universe, then it depends on the constituents, including the cosmological constant. You can measure the characteristic size of the fluctuations that you saw in that microwave background picture and compare it with what you expect for universes of different geometries. And basically, the one that fits more or less exactly is a so-called flat geometry, which is this line here. The CMB gives you something which is almost saying that it's almost flat. Because the size of the fluctuations on the sky resembles this one on the left, if we lived in an open universe, then they would be closer together, and the closed universe that is finite volume would be at a larger scale. But that's not what you see. One of the things that strikes you is that these three colored areas all coincide at this point here, which has an amount of dark matter which is about 20% and about 70% in lambda. Only about 5% of that is baryonic matter. So we have evidence here that there is a cosmological constant, that Einstein didn't make a blunder, and that it's actually the dominant component of the energy density in the universe. So this is the more detailed evidence for that characteristic size, which I perhaps won't explain. So this is the picture that we have. We have a universe which is only 4% normal matter, and 96% of the universe we don't understand. Actually, 100% of the universe we don't understand, because we don't even understand this bit here, because we don't know why it's matter rather than antimatter. we don't have a full understanding of that. So we don't understand any of this. But even if you accept that, well, maybe we do know something about the normal matter, there's still a lot of it that we don't know. So 2 ingredients: CDM, cold dark matter, and lambda, and it's the so-called lambda CDM model. And as my colleague in Durham said, there's only 2 problems with lambda CDM. One of them is lambda, and the other is CDM. But it seems to fit extremely well. So it's a phenomenological model. These ingredients are introduced. They're very simple ingredients, and they basically fit almost everything, and we'll see the evidence for that later. So this is the picture that we have of the expansion of the universe over time. It first decelerates, then accelerates. So the distance between any 2 objects follows one of these lines here. It's convenient because it makes the universe older. If we didn't have lambda, the universe would be younger than the oldest globular clusters in the universe, so that avoids a slight embarrassment. So it seems to work, but let's just explore it a little bit more and say, all right, can we understand what's going on here? Is it really lambda, or do we need to modify the gravity law in some way? On the one hand, and the other is that lambda may be something else. It may not be the cosmological constant. I'll say what I mean by that in a moment. So general relativity has this field equation. This is basically the analog of Poisson's equation in Newtonian gravity. You have something which tells you what the field values, an equation that tells you what the field values should be, which would be the gravitational potential in Newtonian theory, due to sources of that gravitational field, which are mass, or in the case of Einstein gravity, it's mass and energy. And the equation, the analog of Poisson's field equation, is this Einstein equation. So G here is some complicated function of the curvature of space-time in loose terms, and the right-hand side is the source term, which is the energy and momentum tensor. So ignoring these constants, we have basically an equation that relates G and T. And Einstein's modification was to add in an extra term or subtract a term, which is lambda times the metric tensor. So schematically, it's that form. Now, nowadays, we tend to do something slightly different. So one possibility is that this equation is right, and that basically is just how things are. That is the theory of gravity. The other possibility is that we can modify it, but we do something subtly different, which is to change the equation to this. I'll just leave you for a moment to digest what I've done here. Everybody okay on board with that? Right. Okay, good. So, but the conceptual difference is that we now regard this thing on the right-hand side as a contributor to the energy momentum density of the universe. So it's not a feature of gravity, it's some new stuff that's would in some ways allow you to just go back to Einstein's original theory, G equals T. It's just that T has an extra bit. And if we interpret T as a vacuum energy, in other words, if we say, all right, if a vacuum has an energy associated with it, then that acts exactly like lambda. And so we can, if there's a vacuum energy, we can essentially replace lambda by the vacuum energy. Has some strange properties. It has negative pressure and so on. So one possibility is that actually it's not a vacuum energy whose energy density doesn't change as the universe expands. It could be something else that evolves, whose energy density evolves with time, like everything else does. Like radiation will get a lower energy density as the universe expands, ordinary matter similarly. So what this is, nobody really knows. If you look at particles and antiparticles being popped into existence and work out the energy density associated with that, it's about 120 orders of magnitude too big, so that doesn't work. So you then have to have a reason for making it way smaller. So this is one of the big puzzles of why, if it is a vacuum energy, it is so small. I guess how are we doing for time? We should be finishing about 1:30, or how long do I have? About 15 minutes. Okay, I'll maybe skip a few things then. So other more exotic possibilities are that the gravity law is wrong. We modify it in a different way from lambda. And the most exotic one is perhaps that the universe may have more dimensions than the ones that we think of. And the gravity can leak out into those other dimensions, making its form slightly different in our own observable universe. So that's one of the more outlandish perhaps possibilities, but there are many. There are hundreds of modified gravity theories that are not Einstein. So if we're going to ask the question, well, is it really lambda that's doing the acceleration, or is it some form of dark energy that's not a vacuum energy but something slightly different? Then we need to ask, well, what observable things can you measure that are affected by either a new gravity law or a new energy component that's dark energy? And basically, they changed the expansion rate of the universe. They changed the geometry of the universe in subtle ways. They changed the rate at which structure grows. And they also change, in principle, how light gets bent by matter if you change the gravity law. So there's quite a lot of things that we can test. And one very powerful way of testing these is to use gravitational lensing, which is what I do most of the time. So here this is showing time slices as the universe evolves. And of course, when we make observations that go very deep into the universe, we are looking back in time. So we have to consider what the universe was like on our past light cone, during which time it's evolved, it's developed in these rich structures, but the more distant parts of the universe were smoother. And when we make observations of very deep observations, we have to take that into account. So one of the things that happens is that the light from distant objects has to pass through this clumpy universe, and it gets bent by gravity. And so the picture that we get of the distant universe is not quite perfect. And the shapes of distant galaxies are typically altered by around about 1 or 2% because of their passage through the universe. And you can look for those patterns. And if you look at the average shapes of galaxies in different patches of the sky, then you should see these coherent patterns. Now, this is a somewhat extreme part of the universe where there's a rich cluster of galaxies where the gravitational field is very strong. But hopefully you can see that these lines, which tell you the sort of average orientation of the galaxies, tend to be distributed in a tangential way around the masses. Maybe not entirely convincing, but hopefully you can just about see that the lines tend to be tangential rather than radial. So this is just about visible. In other random bits of the universe, you wouldn't be able to see it, but statistically, you can see whether the galaxies' images tend to be aligned, and this is measured with statistics like the correlation function of the shapes, and you can measure it like this. So this is the traditional way of measuring these distortion patterns due to gravitational lensing. And the detailed properties, the theory line here depends on all of the things that we had before, the gravity law, the dark energy properties, and so on. So what's the situation at the moment? Do the data favor a dark energy, an evolving dark energy, or lambda, or some non-Einstein theory? So we can do various things if we assume that the dark energy has an equation of state that's given by this, where the pressure is rho c squared times some number. Then for non-relativistic matter, this number is essentially 0. For radiation and relativistic matter, this number is a third. And it turns out that for a vacuum energy, this number has to be -1. So the pressure is minus rho c squared for vacuum energy. So one of the things that we can test is, can we measure W, and is it -1? If it's -1, that's consistent with lambda. If it's not, then it's some new stuff. So here's results from the dark energy survey showing the current value of W, which is this number here. This is the rate of change of W. And if you put a whole load of things together, then you end up with this purple contours here, in which lambda sits at the crosshairs. So we see that these data show no evidence for the acceleration being due to anything other than lambda. Okay. So that's the current state on lambda. We'd like to get these error bars smaller. We will do in the future, but no evidence for anything beyond lambda. On the bottom, we have some tests, some sort of generic tests of beyond Einstein theories. So essentially, I mean, there are many theories, and you need to test them really individually. But this sort of simplifies things a bit, where you effectively change Poisson's equation from being del squared phi is 4 pi g rho to you should change it for non-relativity by some amount. In fact, in Einstein's theory, there are two potentials that are involved in weak fields. So there's two things here, which if mu and capital sigma are 0, then that's consistent with Einstein gravity. So these are the current values of these two numbers, with a whole load of assumptions, I have to say. But again, if you put everything together, then you find that Einstein gravity, which sits in the crosshairs here, is perfectly consistent with the data. So that's where we are at the moment. It seems that lambda is the cause of the acceleration. There's no evidence for anything more exotic. So it seems that Einstein may be right. We seem to live in a universe with a small non-zero lambda, and nobody really knows why. So that's where we are. Let me just, perhaps in the last 5 minutes, if I rattle through what we're doing to try to improve on those, rather large error bars, which is to maybe I'll skip through to here, which is rather than taking all of the data and reducing it to correlations of shapes, we try to use all of the data and to do a thing called field-based inference, where we don't compress the data into these summary statistics. And the reason that we do it is that if you think about it, when you do an experiment and you confront it with theory, you have a lot of theoretical lines that may vary as you change the parameters of the theory, and you've got some data points with some error bars. You would probably say, well, how do I find the best fit? Well, I would perhaps minimize chi-squared. So now minimizing chi-squared is fine if your data points have errors which are the errors, or they are distributed in a Gaussian way. If they're not distributed in a Gaussian way, then chi-squared is not the right thing to do. And the universe has got so complicated over time that we're not sure that we can assume that any statistics that we have Gaussian distributions. So if we want to do something better, as the data gets better, then we need to use more sophisticated techniques which have the right probability distributions. If you don't have the right probability distributions, you're going to get the wrong answer. So it's possible that the techniques that we use are fine, but we're not sure. So we want to do things which we know are fine, if we can. And essentially what we do is to simulate the early universe, and we essentially find distributions of matter in the early universe which are consistent with the data that we see. So here, this is galaxy data, galaxy number data done by my colleagues in the Aquila Consortium, where essentially what we're trying to do is to determine the initial conditions of the universe, but we want to make sure that the final conditions, the present day conditions, match to within the errors, the distribution of galaxies. So we draw samples of the initial density field, and essentially we, using some quite nifty sampling techniques, we can just choose those initial conditions which are consistent with the data, where we have data. So if you look in the middle here, this is the simulations that match the data. You'll see in the middle the pattern is pretty stable. Out here, there are many possibilities that are compatible with the data simply because there's no data there. So this is very expensive computational work. I haven't got time to go into the details here, but we do the same thing in with gravitational lensing. And what we're doing is exploring an extremely high dimensional space. So to go from the initial theory to the observation, there's a whole load of numbers that are part of that. And those are the true density in the universe everywhere. So in order to solve the problem properly, we need to work out what the density of the universe is everywhere between us and the galaxies whose distorted images we look at. So we basically have to determine about 1 million numbers. So you're maybe used to having models where you adjust a couple of parameters in the theory. We have to determine, upwards of 1 million at once. And there are sophisticated ways based on Hamiltonian Monte Carlo sampling that we use. So maybe if I just skip that and show this one. So this shows where we allow the density of matter to vary and the clumpiness of the universe. These are the initial conditions, which are then evolved to the final conditions, which we then compare with the lensing signal. And basically, we keep only those which are similar enough to the data to pass. So what's the advantage of doing it this way? It's very expensive. It's very time consuming. A lot of computer time involved. But if you compare what we can learn about this is not directly about the dark energy, but the amount of matter in the universe and the clumpiness of the universe, then with traditional techniques based on correlation functions and so on, you tend to get restricted to the banana shapes like this. So we can't tell where we are on this banana very easily. But if we use these field-based techniques, then this is all with simulated data at the moment, then this banana collapses down to this blue block. And this is using this thing called the Bayesian hierarchical model. And this is quite powerful. I mean, if you look at the error bar on the matter density, we reduce it by a factor of 5 by doing it this way rather than by taking the traditional approach. So the idea is that we will be applying this to the dark energy properties, to the gravity properties with much better data, which is coming from Euclid in a year or two, where the data will be fantastic. And so we are trying to upgrade the analysis side of things so that we can get every ounce of information out of this. And we need to, because the differences between what you expect from lambda and from dark energy, which is not vacuum energy, are very subtle. They're very small. So we need to make sure that we can tease out all of the information that we have. So let me just finish by saying, just sort of summarizing what I said a minute or two ago, that at the moment, the evidence that we have is that Einstein didn't blunder, that the cosmological constant does appear to be a feature of the universe. We don't know what it is. We don't know what the dark matter is either. And he said once that everything should be made as simple as possible, but not simpler. And I think that's the situation that we're in here. We can't make it simpler than removing lambda because it doesn't fit the data. So this is the simplest that we can go. But all the evidence at the moment seems to point to the universe being actually relatively simple. It just has these two new ingredients, which themselves are rather simple in terms of their properties, but what their nature is, nobody knows. I'll stop there.